In Salesforce development, business logic starts simple. A single rule, like routing a VIP account, takes 2 lines of code. But within a year, as edge cases pile up, that single rule mutates into a dozen nested if-else branches. This organic growth creates a massive, tightly coupled block of execution code. Every time you touch this file to add a new tier or adjust a parameter, you introduce severe regression risk to every other rule inside it. It also creates a unit testing nightmare. To validate one minor branch of logic, developers are forced to construct extensive data contexts and mock platform behaviors just to navigate the maze of conditions. If you have to edit the core method to add a new rule, the class is never truly closed to modification. This structure inherently violates the open-closed principle. Relying on nested conditional branches creates a structural liability that prevents safe scaling. The solution is the strategy pattern. This architectural design defines a family of algorithms, encapsulates each one in its own class, and makes them interchangeable behind a standardized interface. By treating the algorithm as an independent object, you can entirely swap the execution behavior without touching the code of the system requesting the work. We are going to build this engine from first principles. We will model the base components, optimize the execution to survive Apex governor limits, and automate the entire selection process using custom metadata. This approach eliminates fragile programmatic branching. The monolithic file is replaced by isolated, modular components. This is the strategy interface. In a pricing engine, this I-discount strategy interface defines a strict mathematical contract. Every pricing rule must implement this exact apply discount method. Beneath the interface are the concrete strategies, individual classes like standard, VIP, and educational. Each of these classes holds its own unique calculation algorithm. The VIP math is entirely isolated from the educational math. They share no variables and contain no overlapping logic. When the business eventually requires a partner tier, you don't edit an existing file. You write one new class that adheres to the interface. By pushing the logic into independent files, the size of any single class remains permanently bounded. The code stays predictable and easy to read. The final component is the context class, the system's execution hub. Notice it holds an empty slot shaped for any I-discount strategy. We populate this using constructor injection. A specific concrete strategy, like the VIP class, is handed directly to the context from the outside. The context does not know how the VIP discount is calculated. It merely calls the execute method on whatever strategy it currently holds, passing through the original card amount and returning the result. The context delegates all the mathematical work, containing 0 internal if-else decisions. This achieves perfect decoupling between the caller and the calculation. Moving from pricing to compliance, the pattern works the same way. Consider routing leads. European leads require strict ownership assignments to comply with GDPR regulations. Meanwhile, leads from California must follow localized CCPA rules, requiring routing to entirely different user queues. A developer might naturally write a concrete strategy for each region, placing a SQL query inside that strategy to fetch the exact regional queue ID. Executing this strategy inside a bulkified trigger loop multiplies that single query by 200 records. This instantly shatters the 100 query governor limit and halts execution. Blindly applying object-oriented patterns without factoring in Salesforce bulkification rules will break your production environment. This introduces an absolute rule for Apex implementations. Never put SOQL or DML inside a concrete strategy that runs in a loop. This diagram shows the architectural solution. Prefetch all required external data, like QIDs, into a static map before the execution loop begins. That data is then injected into the strategy via its constructor. The state is handled before the logic fires. With state removed from the strategy, the execution method operates strictly on data already in memory. This solves the N+1 query problem and ensures the logic scales efficiently within Salesforce bulkification limits. We still have one remaining architectural flaw. If the code calling these strategies uses a switch statement to decide which class to instantiate, the open-closed principle is still broken. We solve this by introducing the factory pattern. This centralizes the object creation process, removing the instantiation logic from the context entirely. We bridge the factory to custom metadata using a table mapping a text string, like VIP, to the exact Apex class name. The factory reads this data and uses type.forName to instantiate the class, dynamically spawning the strategy and bypassing manual coding. This creates a zero-touch extensibility model. When a new rule is needed, you write one isolated class, insert one row of metadata, and the codebase remains untouched. The greatest immediate return on investment for this architecture is the radical simplification of unit testing. Look at this comparison. On the left, a traditional testing method requires inserting accounts, generating dummy-related records, and fighting validation rules. On the right, the code needed to test a pure concrete strategy. Because the strategy is logically isolated and entirely in memory, you supply a single input value and write a single assertion for the output. Robust unit testing requires minimal effort when the architecture enforces strict boundaries between data retrieval and algorithm execution. To implement this successfully, follow 3 rules. First, default to constructor injection over setter injection. This guarantees your context object is never trapped in a null state. Second, implement a getStrategyName method within your interface. This ensures your production debug logs explicitly identify the exact policy that ran. Third, banish SOQL and DML from the execute method to ensure bulk-safe operations. Composing strategy, factory, and custom metadata creates a system where business rules are extended through metadata and isolated classes. This allows the core execution logic to remain stable as the organization's requirements grow.